Hello, everybody. In today's live, we're going to go over what we were talking about yesterday. We're going to continue with improper integrals. We're going to cover the more difficult type of improper integral now, which is type 2 integrals. We went through a lot of details yesterday about type 1 integrals. Let me share that actually. So, looking at this, we covered a lot yesterday about how to deal with type 1 improper integrals. Remember, what's a type 1 improper integral? It's where the infinity is in the input, right? So it's in the bounds of the integral, basically, as we're seeing here. So here, there we go, bounds of infinity there, infinity there, infinity there. So you can see the infinity in the input. Here there are two infinities. These are all type 1 integrals. These are the easier ones. The ones we're going to talk about today are type 2 integrals, or improper integrals. And we define that yesterday. They look kind of like this. There's an infinity, but it's not obvious. It's in the output of the function, not the input. And for that reason, it's not really obvious, for one. And secondly, it's yeah, it's not obvious. And then even after you discover it, it's a little bit more complicated than the type 1 improper integrals. So here, let's actually go over this today. So let's start with this problem. This is a good example. So the first thing, and actually, let me grab the process from yesterday. So this is actually the same process. That's the good news. Like this is the process for any improper integral. The difference is that this step is really more complicated. And you could argue there's actually a step 0 beforehand. It's basically identify where the infinities in the output are. You could argue that's an additional step. But so it's the same basic steps, but again, you could argue there's an initial one that you didn't have with type 1. And honestly, on that note, the hardest part of these is even recognizing that it's an improper integral, right? Like if you just look at this thing and your brain is not primed to think, oh, this is an improper integral, it is very, very easy for you to miss it. It's very, very easy for you to just think it's a regular integral and just solve it normally, right? So you might think, oh, let's just jump into this. This is going to be -1 over x between 1 and -1. What is that? -1 over 1 minus uh or minus -1 over -1, so minus +1. So you might think the answer is just -2. That is wrong. That's what it would look like based on everything you've learned about integrals up to this point. But these are very sneaky, right? They're not like type 1 integral improper integrals. You see an infinity in the input of those. Here you do not see the infinity. You have to think about it and check for it without being reminded. That's honestly the trickiest part of these to even recognize. That's what I mean by step 0 here, to even recognize that it is an improper integral. So, how do we actually do that? Basically, and this is kind of unfortunate, the only way to be sure that you never miss one is for every integral you do, for every definite integral, right? This is definite integral because it has the bounds. For every definite integral that you do for the rest of your life, basically, you need to make sure it's not improper. And how do you check that? Basically, ask if there are any vertical asymptotes within your bounds, and that's important. You're allowed to have vertical asymptotes outside of your bounds. That's actually not a problem. It's only a problem when you have vertical asymptotes within your bounds, between the -1 and +1. So if you think about it, how do we do that? Basically, you just see where the denominator is 0 and the numerator is not 0. It gets kind of complicated, but normally you don't really have to worry about that part. Technically, when they're both 0, numerator and denominator, you could have a situation where there's basically a hole, right? There's basically a hole in the output. So with those, again, depending on the situation, maybe the integral exists, maybe it doesn't. That's very rare. Most of the time, it's as simple as saying if the denominator is 0, there's an infinity there. But technically, yeah, the numerator has to be non-zero for that to be true. And then here, like in this one, hopefully you can see, I mean, if we just set, like, what's the denominator here? X squared or x squared? Let me actually pull this down. So remember, that method above is wrong. We can't do that because this actually is improper. And this is kind of the unfortunate part, by the way. It's almost like, here's what I'll say about type 2. Like type 1 improper integrals, you can get those right 100% of the time as long as you don't make algebra mistakes. But you can identify the problem, and it's like, it doesn't really change the process. There's an argument, and honestly, there's like an argument for getting type 2 improper integrals wrong sometimes. Let me make the argument. you've probably done hundreds of integrals in your life, or maybe thousands, depending on what exact class you're in and how rigorous your classes have been. You might have done hundreds or thousands of integrals. Technically, based on what we're saying, the reason you've never had to do this step zero before, remember, like identifying like infinities in the output, like checking that before going into the work. Usually you probably just see something like this and you just jump right into the work, right? And that's more efficient if you can just kind of build the muscle memory and you don't have to think about it. You can just go straight into your work. But with this, I guess what I'm saying is technically for every integral you do for the rest of your life, if you want to be the most accurate, you do need to check if it's a type 2 improper, right? Obviously, if it's a type 1, you'll see an infinity in the bounds. That'll remind you, oh, wait, this is improper. I got to do this differently. But if you don't see an infinity in the bound, it could be a normal integral, a proper or a regular integral, or it could be a type 2 improper integral, the one we're talking about now. And then there's no way to know, right? There's no way to know without checking. So you could add an additional step. The step 0, you could add that to every integral problem you do for the rest of your life in order to really know, right? The reason you haven't had to do it so far, right? If you're just learning about improper integrals in class now, the reason you haven't had to do it yet is because up to this point, your teacher has in your textbooks and your quizzes, everything, they have essentially cherry picked integral problems to make sure they are not type 2 improper integrals. But technically, if they weren't cherry picking, you should have been checking to see if they were on every problem you do. And this is kind of an issue because it sounds like a small thing. Okay, we just do one more step. But yeah, you're going to be doing one more step on hundreds of integrals that you do for the rest of your life. That's kind of a lot of work. And to be honest, 99.9% of the time, the way it typically works out, again, every one of those could be a type 2 improper integral, but usually they're not. Like 99% of the time, they're not. So honestly, there's an argument to just get them wrong when they show up. Like to not check it, unless obviously if you're taking an improper integrals test, then check everyone, right? Because they're very likely to show up. But when you go to take the AP exam at the end of the year, honestly, I kind of have the opinion that it's better to just get the type 2 improper integral problems wrong and not check. That might sound like a controversial opinion, but the argument for it, and again, it all depends on how fast you move on the test, right? If you have plenty of time on the test, okay, then we can add steps to every problem and you can check every problem. If you want to get truly a perfect score, you'll still get a 5 even if you don't get anywhere near a perfect score. Like there's a lot of room for error actually. But if you really want to get the best score you can, then you have to do this for every integral that you ever do for the rest of your life. But I guess what I would say is it's almost better to just get one or two problems wrong on the AP exam if they show up at all. Type 2 improper integrals. Type 1 will definitely be on the exam. But like type 2, there's a good chance there will be one, it's anywhere between 0 and 2 questions on the exam. And they won't be FRQs, or at least if they are, there'll be one part of it, which is highly unlikely. But it could happen. So that's kind of the idea. Again, I'm not here to tell you what to do. I'm here to tell you here are all of our options. Here are the costs. Like everything we do has a trade-off. Hopefully I've explained the trade-offs enough. But I actually kind of recommend, I personally kind of lean towards when you're taking your improper integrals test, yeah, then you obviously need to check everything because your brain's primed for that, right? You're on the lookout for improper integrals, type 2 improper integrals and type 1. But after that test, I kind of, unless you're dealing with like cumulative tests after that where they like really show up a lot, if you just have to worry about it for the AP exam, I almost kind of prefer that you just get the problem wrong and you just do because like the cost of it, you know what I mean, is like it makes you slower on every other integral problem you do. And like 98, 99% of the integrals you do are not going to be type 2 improper integrals. So it's almost better just to get 1% of them wrong to be faster on the 98 or 99% than to like slow down the 98 or 99% with like extra steps and checking to get the other one right. So there you go. There's my recommendation. It's pretty nuanced, but either way, if you want to get it correct, you do need to check that. So here, when we look at this, you basically just set the denominator equal to 0, right? So what x value would cause this to equal 0? Hopefully it's clear. X equals 0. So we know we have an infinity or a vertical asymptote at x equals 0. Now the next question, is 0 between the bounds 1 and -1? Yes, it is. That's why if we were taking the integral of this, so just to check or just to test this out, let me actually Just a second. I'm gonna get the same animation that I've been using the last couple days just to visualize these. And you can check it out on your own as well. So if you check this out, so basically if we're talking about, in this case, 1 over x squared, if I'm integrating from basically -1 to +1, that would be a type 2 improper integral. You can see that's undefined, right? So it's actually divergent because we have that infinity in the middle. We have that first class asymptote. So it's really going to be an infinite amount of area. It's just going to go up forever and never stop. So hopefully that makes sense. But, or if I can go back to the beginning, there you go. If we had both of these on one side, now it's not a problem. Now it's not even an improper integral anymore. There's no infinity in the output. So now it's just a regular integral and you're good to go. It's a regular finite area, no problem with that. Or if you put that one over there, there's no problem. There's only a problem if the infinity is in the bounds of your integral. That's the only time there's a problem. And as soon as that happens, it becomes a problem. Now, what we'll do here, we'll actually talk about a couple different use cases because we'll build up. So actually, I changed my mind. As we talk about this, let's actually tweak the lower bound. Let's talk about this because this is still an improper integral, a type 2 improper integral. So that would be kind of like if we go from 0 to 1. So that's kind of what we're talking about. And you can see, obviously, the answer is already undefined. So we kind of already know how this is going to turn out. But we'll build up in the complexity here in a second. So basically, for step 0, you have to find all the infinities where the denominator is 0, basically, and the numerator is not 0. And then the next question is, are those x values where we have an infinity in the output either on the endpoints or in between the endpoints? If it happened, like here, you can see I just tweaked the problem. So 0 we know is the problem point, and now it's one of the endpoints. That still counts. Like you can still have problems with that, and in this case, you will, as you'll see. So basically, that's step 0. You have to check that first, and theoretically, again, I've already given my speech about how you kind of technically have to do this on every single integral you do for the rest of your life, but also it's not going to be that bad if you don't do it. It's like you just get it wrong very infrequently. It's almost a cure worse than a disease, I feel, to check this on every test for like a typical exam. And then here, so that's step 0. And now step 1 is kind of similar to before, but it's a little bit different. There's a little bit of a tweak. So again, we still have a problem point here. What's our problem point? 0 in this case, right? That causes an output of infinity. So we're still going to replace that. So there's going to be an a there. There's going to be a 1. We're still going to have this expression, right? This should look pretty familiar. But the difference is we're not going to take the limit as like when we were doing type 1, it would have been as a goes to negative infinity. That's not what we're going to do. We're going to say a goes to the problem input. Now, this is where you got to be a little careful because when we're not talking about, so here's what I'll say. When you're talking about negative infinity, it's automatically implied that you're approaching from the right. You have to, because you can't approach negative infinity from the left. Negative infinity is supposed to be the most negative number possible. So the only way you could get close to it is coming in from the right. Whenever you say limit as x goes to positive infinity, it's always implied that you're implying that you're coming in from the left. Because again, same argument backwards, right? If infinity is the most positive number that exists, so it's not possible to come in from the right. It's not possible to have a number bigger than it and approach from the right. You have to approach from the left. That's implied. When you're talking about a finite number, it is not implied because it could be either. So like if we're talking about 0, we could be coming in from the left, right? We could be coming in from the left if we're coming in this way, or if we're coming in this way, we could be coming in from the right. And basically the rule is, again, if you don't do this step, you will probably get it right, but there are some cases where you'll get in trouble with it. So basically the way I would say it is if it's a lower bound, you always approach from the right. If it's an upper bound so here we replace the lower bound, so we got to approach from the right. Doesn't that make sense if you look at it visually, right? So in this case, basically what's happening is that we're gonna come up with an expression for a here, and then we're gonna take the limit as a approaches 0. But because it's a lower bound, you see how we have to be approaching from the right to get to 0? That's what's happening. Whereas if it was reversed, we'll talk about this in a second as well. But if it was reversed, if you approach from, like if it's an upper bound, you have to approach from the left. So that's the rule. If it's an upper bound, you approach from the left. If it's a lower bound, you approach from the right. End of story. So there you go. That's that. And now we're that's step one. So this is really the part where it gets more complicated. The rest of it, like steps 2 and 3, are not more complicated. I would say they're basically the same compared to type 1 integrals. At least I'm not saying these are easy. I'm just saying it's not much harder than type 1. It's really the same process from here on out. So let's actually give that a try. So if I come down here, let me pull this down a bit just so we don't have to keep scrolling. So if we're looking at this, then solve the integral normally. So 1 over x evaluated between 1 and a, and we still need the limit here, limit expression. And then how would this go? So we get -1 minus -1 over a, which is really plus 1 over a. And now solve this limit. There we go. We evaluated the integral at this point. Now we solve the limit, -1. So here, what happens as the denominator approaches 0 from the right? So like 0.1, 0.01, positive, 0.001, 0.0001. I mean, hopefully you can tell that this thing's actually going to blow up to infinity. So the whole thing will blow up to infinity. That's why we get diverge. The diverge is the answer in this case. And that's why, by the way, when we were doing this method, that's why Desmos tells us, like Desmos already told us it's undefined. So there you go. You could do basically the exact same thing. Again, I won't go through the lot. I'll go through step 0 and step 1. But like if we want to do the next one, it's essentially the same process. Let me tweak the bounds first. So if we're talking about now from -1 to 0, how would we do that? Basically, again, here's the problem point. So we need to replace that. So it's going to be limit as b approaches 0 from the left. And then -1, 0, 1 over x squared dx. I won't work it through the rest of the way. It'll turn out essentially the same way. But you can see that if we set a to -1 and then b to 0, that's a problem. So this is the simpler case, I'll say, when, I guess, how should I word it? This is the simpler case when you have I guess, how should I word it? Basically, when you have the problem point, like 0 in this case, on one of the bounds. And that's more straightforward. It's a little bit less straightforward when you have it somewhere else. So let's take a look at one of those. Let's go back to the one that I was originally going to talk about. That's a little bit more complicated. What if we're going from -1 to 1? So now the problem point is actually not on one of the bounds. The problem point is in the middle somewhere, right? The problem point is 0. That's between -1 and 1, obviously. What do we do there? The key here is that we have to essentially split this integral using, it's very similar to the last one we did yesterday, remember? So if I go back to yesterday, what did we do on this one? When you're dealing with a type 1 improper integral and you have infinity on the upper and a negative infinity on the lower bound, you need to split it in the middle. Here, it's kind of similar. When you have the problem point, here we don't have, obviously it's type 2, so we don't have infinity in the inputs. But if you have a problem point that causes an output of infinity in between those endpoints, you actually have to split the integral at that endpoint and then do the techniques we talked about before. So step 1 on this would be, again, identify the problem points, but then we need to do we need to split it basically. So go from -1 to 0. And then for this next one, go from 0 to +1. And from here, we can do the same process above, because now you see by doing the trick where we split it, now we are forcing the problem point to be on one of the endpoints. And we just talked about how to handle that above. So it'll essentially be 2 separate integrals, right? This one has a problem on the upper bound. So limit as b approaches 0 from the left, integral -1 to b, 1 over x squared dx, right? So we get that plus limit as a approaches 0 from the right, integral from a to 1, 1 over x squared dx. And then we basically already did these problems above. We know they're both infinity. If even one of them is infinity, if one of them's fine, if one of them converges to a finite number, but the other does not, the other goes to infinity, the whole thing's wrong. The whole thing's infinity. So diverge. So, and that's why you can see here, when I actually do this, this is what we were originally looking at. Desmos says is undefined, that means diverge. I wish Desmos was smart enough to just say diverge. That would be better because that's how it's used. That's how they want it presented in a typical class. But there you go. Hopefully that process makes sense. That, like I said, these are more complicated. These are type 2 improper integrals. The biggest thing, honestly, like the mechanics are slightly harder than type 1 improper integrals. The real thing that's trickier is like even identifying them as improper integrals. So that's the one where you have to be really careful. Now, what I would like to do, I would like to show you some examples. Let me try to find an example. I want to show a type 2 improper integral where it actually converges. That's what I'm looking for here. I know we've talked plenty about type 1 improper integrals. Let me see if I can find one where it converges. Okay, so this is going to be a little bit trickier to evaluate, but this is one. And I know I already told you that it converges, but we still want to calculate what it converges to, right? So here, let's give it a shot. So here, this one, again, this probably looks a little bit more intimidating than the last one we did. But just to show you, because this is a weird idea. It's kind of a weird idea that we can have division by 0. We can effectively have an infinity somewhere, and it could still work. So let's just solve this one, and then we'll talk about how to solve it, or we'll basically look at some like a visual of it and see if what we got makes sense. So to start here, first question is how do we integrate this thing? We need to identify the problem points, right? So what's the problem point? If you think about it, what would cause the denominator to be 0? 2 and negative 2. 2 and negative 2 would be the problem points. So here, if I come down to here, yeah, remember, this is the process that we're following. So when we're talking about problem points, these are the problem points. Now the next question is, are those in the bounds, like including the endpoints? And the answer is negative 2 is not. That's not between 1 and 2, but 2 is one of the endpoints. So that's the problem point. So we need to pull that out. Now we're doing step 1. So we're going to do limit as it's the upper bound. So I'll say b. You don't have to say a and b. That's just a convention. So we go from positive 2, approach positive 2 from the left. Remember, this does not mean approach negative 2. That would be negative 2 right there. The negative or positive here tells us coming in from the right or the left. And you'll see why this is important, actually. I don't think it'll make a difference it might make a difference in this problem. But I don't think it will, but we'll see. And then I'll rewrite the integral. So integral from 1 to b, and then 4w over the cube root of w squared minus 4. dw. And then basically we're going to set u. The way you solve this is, or at least it seems to be with u sub. Again, this might be a little bit trickier, and it seemed, well, yeah, I'll just leave it at that. It seems like this one, this is obviously more tricky than the last one, but as long as you recognize that it's u sub, it's not too bad. Basically, if we choose the inner function, what would be the only reasonable choice of an inner function here would be that. The derivative, think about what the derivative of that is, 2w. Are we multiplying in the numerator by something proportional to 2w? Yes, 4w is proportional. So that's how you know u sub will work. And then du, again, I made other videos on u sub where I dive into that in a lot more detail. So feel free to check those out. I would recommend that. But here, I'm just going to kind of blast through it a little quicker because I want to show off the improper integral part. That's the main thing I want to talk about. So there you go. That's our u substitution. Now let's actually do the u substitution. So it'll be, and this is where you have to change the bounds, right? So 1, what's that going to become? It's going to become negative 3. B, what's that going to become? You kind of need to leave it as a formula, b squared minus 4. You just plug in w equals b into this equation. That's the best we can do, because we don't know what b is. It's a formula, or it's a variable in a formula. And then we have 4w over the cube root of u. So the cube root of u times dw, which is du over 2w. And then we would take the limit as b approaches 2 from the left. And then here, this better happen. If the w's don't cancel, that's a problem. We need them to cancel. And then after that, we have something that's actually completely doable. So we have 4. So we have you got to be careful. We have a 4 over 2. So we're actually going to end up with 2 on the outside. Negative 3. b squared minus 4, 1 over the cube root of u, and then du, like that. So, all right, let me tweak that slightly. So looking at this, now we need to integrate. How do we integrate? 1 over cube root of u, that's, think about it, u to the negative 1/3. How would we take the antiderivative of that? Add 1 to it, so positive 2/3, and then 1 over 2/3, which is really 3/2. And remember, we have the 2 on the outside. Those will cancel. So we're really just going to end up with 3, apparently. And then we're going to evaluate between negative 3 and then b squared minus 4. So hopefully that makes sense. Let me clean it up a little bit. Again, I know I'm kind of blasting through this. I'm not trying to focus on the actual integration itself. Like, that can get complicated, but that's handled by all the techniques you already know, basically. That like the improper integral section doesn't add anything to like how do you integrate. It assumes you already know all the techniques to integrate and you've already kind of mastered those. And it's like, okay, oh, by the way, when you're doing those techniques, here's an additional curveball. Maybe there's an infinity somewhere and you have to learn how to deal with that. So that's why I'm not going into a ton of detail here, but hopefully you're following. And then if we plug this in, think about what this would be. Basically, we can, basically we can just plug in the values, right? So u equals this thing. So we're going to get 3 times b squared minus 4 to the 2/3 power minus 3 times negative 3 to the 2/3 power. So hopefully that makes sense. Again, I've already said that it converges, but let's see if that makes sense. So here, does this converge? Well, here, where's b? There's b. What happens if we get really close to 2 from the left? And sometimes the side from the left or from the right matters because that's the only spot the function is defined. Think about it like if you think of the function square root of x and you're approaching like 0, you from the right, you can do that, but you cannot approach 0 from the left because that's outside of the domain of the original function, right? You can't have, like, if you're dealing, like, just to reiterate, if you have square, I'm just making this up. This is a separate problem than what we're dealing with. But if you have like something like this, and you had limit as x goes to 0 from the left, that's not valid because that would imply that 0, like x is like negative 0.0001, aka a negative number. You can't have a negative inside of a square root. So that's where this would come in handy. Like, that's where that would like actually be an important detail. Whereas if you had it from the right, that's completely doable. That's doable because like you can have positive numbers on the inside of that. So that's just one example of where that might come in handy. But for our problem, it doesn't actually matter. It doesn't matter whether we plug in 1.99 or 2.001. When we square it, it's going to get infinitely close to 2. So we don't have a domain problem here. So in this case, that's why I say, like, when you deal with this, it usually, like, if you get this wrong, you'll probably still get the right answer. Like, this is a good example of that. But there are some problems where you'll run into some trouble. Maybe. But anyway, if we do that, we can basically just plug in positive 2 to right here. Think about what that will be. This whole thing will be 0. And this is important because 0 is now in the numerator, right? We have a positive exponent here. If we had a negative exponent, that would be a different story. Then we'd have 0 in the denominator, and this thing would diverge to infinity. But because it's a positive exponent, this whole thing's in the numerator. That's fine. That means that's 0. That's completely acceptable. We can have that. And then if you think about this, what do we have? Negative 3 times negative 3 to the 2/3 power. If we did everything right, this should be our answer here. Now, there are other ways you can represent this, by the way. Like, if you just use exponent properties, think of it like this. Think of it like, because the thing that's interesting is that these are the same, right? If this was a different number, if this was like negative 4, okay, that's one thing. They're just different numbers. You can't really simplify. But because they're the same number, algebraically, you can actually simplify if you think about it like this, and you use your exponent properties. If I have something to a certain power times the same thing to a different power, that equals that thing to the sum of the powers, 1 plus 2/3. So think about 1, 3/3, 3/3 plus 2/3, 5/3. So long story short, I guess I'm saying the answer is negative 3 to the 5/3 power, which we can evaluate. Now, you have to be careful. If this was squared, you can't have a negative number on the inside. But if it's an odd fraction, so like another way you can think about this, by the way, is the third root of negative 3, the whole thing to the 5th power. So yeah, hopefully that makes sense. But yeah, I'll just say it's not a problem. Whenever this is odd, you are allowed to have negative numbers inside of that root. You just can't do it when it's even, like second square root, fourth root, sixth root, etc. So anyway, this should be our answer. Let's see if that's right. Let me grab the original integral that we started with. So actually, let's pull this down. So this was the original integral that we started with. When I graph it, I'll just do x instead of w. But here, what was it? It was 4x over the cube root of x squared. So the cube root of x squared minus 4, like that. And then where are we going? We're going between 1 and 2. So we're going between positive 1 and then positive 2. And I get that. What is that? It should be the third root. So it should be negative 3 to the 5/3. Let's see if it is negative 3 to the 5/3. Voila, it's the same. So, and it's acceptable. So this is kind of a weird idea, right? Because if you look at it, just to be 100% clear, there is absolutely, if you look at this, there is absolutely a vertical asymptote here. So if I just actually, let me do this. Yeah, I know this diagram's a little bit crowded. Let me actually pull it up on another diagram. So if I just graph this same function here, or whoops, if I just graph this same function, there is absolutely a vertical asymptote at x equals positive 2. Like you can kind of, hopefully you can kind of see that there, right? We will just go down forever, like with no end. We'll just go down forever with no end. There's a vertical asymptote here. But even though there's a vertical asymptote here, again, it's kind of like the same thing as before. Remember how we were talking about when we were doing the type 1 improper integrals? If the function shrinks fast enough, even though you're going to the right forever, it could still get to the point where it shrinks so fast that the area you're adding, even though you're always adding positive area, it's never enough to flip the decimal place beyond some upper limit. So there is actually an upper limit, even though it keeps growing forever, technically. This is like the same thing, but it's happening vertically now rather than horizontally. As we go down forever, as long as like the function is like getting really, really close to the edge fast enough, it's like the same exact. It's like basically the same geometry, but just vertical. So even though we have a vertical asymptote, that is not a guarantee that it doesn't exist. To be clear, it could still exist, and it does. So there you go. Hopefully that makes sense. Now, what I'm curious about, I think the answer would be it does, but let me actually test this. What if we go to another value? So what if we go outside of it? Let's see if it's converges or diverges. We haven't really tested that. But there you go. Even if you go over here, right? Even if you have a vertical asymptote on both edges, right? If I want to integrate this thing from 1 to 3, Desmos is saying that it does converge, right? And you can kind of see it actually, right? It's like, again, it's kind of subtle to see, but I don't know about you, but to me, it looks like this vertical asymptote is like really shrinking kind of quickly. Like it's like the edge is pushing up against it quickly. Again, it's kind of hand wavy, honestly, but compare it to like 1 over x squared. I don't know. To me, if you look at that, it seems like we have a lot more room here, right? And actually, let me do this. Let me plot what we just had. So if you compare that to just 1 over x squared, you see how like when you're talking about this vertical asymptote, like I don't know about you, but to me, it looks like the distance from the 0 to here is like 4 times, or maybe at least 2 or 3 times as big as the gap here. So it kind of makes sense, right? We're approaching a vertical asymptote, but we're shrinking. Apparently, we're shrinking horizontally now, a lot more rapidly. So that area is closing a lot more. So it's essentially the same logic. So I don't know. Again, it's hard to tell where the cutoff is exactly. So I'm not saying you can solve these by looking at them. You absolutely cannot. You have to go through the process. But when you graph it like this, it's kind of believable to me that the one on the right, it definitely can't be reversed. It definitely can't be that the one on the left, the 1 over x squared, is converges, whereas this one diverges. That I'm sure of, because here this one like squeezes a lot faster and a lot more significantly, right? It basically looks like a line here, whereas here we still have a pretty big gap. So it's believable to me at least that this one converges, whereas this one doesn't. So that's what we're doing here. So there you go. That's type 2 improper integrals for you. I would say it's about 10 to 15% harder than type 1. It's like not so much worse. It's really just identifying that you're even dealing with type 2 improper integral, and then maybe a little bit more work to set up the limit. But other than that, it's basically the same process as last time, as long as your fundamentals are solid. So there you go. Hope that makes sense. That's our deep dive into type 2 improper integrals. If you guys have any questions, feel free to just drop them in the chat, drop them in Skool, or just make a post in Skool, and I'll record a short video kind of walking through as soon as I see it. But otherwise, if nobody has any questions, hope that was helpful, and I will catch you guys tomorrow. See you.